Okay, so I'm going to do an introductory video to Feynman diagrams. So first thing, it's Feynman, not Feynman. I know it reads like it should be Feynman, but it's named after Richard Feynman, and he designed these to help convey some of the information about particle physics nice and easily, especially to do with interactions. Okay, so first things first, the Feynman diagram is on two axes. So in the vertical direction you've got time, and on the horizontal direction you've got space. And those become important with the way you draw Feynman diagrams. So let's have a look at an example for electromagnetic interaction. So first thing you need to know is that electromagnetic interaction occurs instantaneously. So the interaction line will be represented by a horizontal line, not an angled line. And obviously electromagnetic interaction occurs only between charged particles. So let's have a go. Let's put two charged particles in, and I'm going to use protons. So you've got your proton there coming in, and obviously protons are positively charged. And let's do another proton, again positively charged. Now when I said horizontal interaction line, the interaction line is like a wiggly line to demonstrate the exchange of a particle. And as we know, for electromagnetic interaction, the exchange particle is a virtual photon. So let's just quickly label that in there. Okay, so key things you should know about a virtual photon is it has zero rest mass and it has zero charge. So there's a couple of key points there. So coming out of it, what do you have? Well, electromagnetic interaction doesn't actually change particles, it just obviously has an effect on them. So you'd still get two positively charged protons leaving, but obviously they would have exchanged the virtual photon, which is like a force carrier, so they've had a slight repulsion, so you'll see them angled away, just like on this diagram. Okay, so let's have a look at another example. This is beta plus decay. Now, decay is caused by the weak nuclear force. So, a beta particle we'll use for beta plus is actually going to be a proton. So we have our proton coming in just as before. So protons are obviously a type of hadron, so they don't interact through the weak nuclear force, they decay through the weak nuclear force. And protons are made up of, just a little bit of extra information, up, down quarks. And weak interaction causes one of these to change into another one. So one of these up quarks is actually going to become a down quark. So now it becomes up, down, down, which is a neutron. Okay, so what we have coming out of it is a neutron, which obviously has no charge. So one of the key properties in the universe, charge, in all types of interaction and reaction stuff, charge is conserved. So there must be another particle coming off which carries that charge, so that charge is conserved because it's +1 at the start, and obviously it needs to be +1 at the end. So when we do our interaction line this time, you must be giving off a charged particle, and it must be positively charged, which means it's your W+ boson. So this interaction, a decay, occurs over time, which is why the interaction line is angled slightly up to show the passage of time. So what happens next? Well, the W+ boson itself decays into two particles, so it forms a E+, or it's often called a beta+ particle, and also in terms of that you get a neutrino being formed due to the conservation laws, which I talk about in another video. So that's a Feynman diagram for beta plus decay. So you can see a decay occurs over time, that's why the interaction line is angled upwards.